Right now, at this exact moment, there are two machines in interstellar space. Not one, two. Most people know about Voyager 1, the farthest human-made object ever built. The spacecraft that crossed into interstellar space in 2012 and has been sending back data from beyond the edge of our solar system ever since. The one with the golden record, the one that keeps making headlines, the one that everyone talks about. But there is a second spacecraft out there, quieter, less celebrated, less talked about. Moving through the darkness 13 billion miles from Earth in a completely different direction, sampling a completely different region of interstellar space, carrying something that Voyager 1 lost before it even reached the heliopause. Something that turned out to be the single most important instrument for understanding what lies at the edge of our solar system. It is called Voyager 2. And what it found when it crossed into interstellar space, what its unique, one-of-a-kind instrument measured as it passed through the boundary that no model had ever correctly predicted, did not just confirm what Voyager 1 discovered, it contradicted it. It complicated it. It raised questions that Voyager 1, for all its extraordinary achievements, simply could not answer. Because Voyager 1 was blind to the most important thing at the heliopause, and Voyager 2 was not. And right now, in the summer of 2026, Voyager 2 is about to become the most important spacecraft in the history of this mission. Not because of what it found, because of what NASA is about to do to it. A procedure so risky, so unprecedented, so all or nothing in its design that the engineering team nicknamed it the Big Bang. A simultaneous, coordinated reconfiguration of every remaining power system on the spacecraft attempted across a communication delay of more than 16 hours each way with no backup plan and no second attempt if something goes wrong. If it works, Voyager 2 gets more time, and everything Voyager 1 will attempt in July depends on whether Voyager 2 survives what happens first. Stay with me, because this is the story most people have never heard, and it matters more than anything currently being discussed in the Voyager mission. Voyager 2 launched on August 20th, 1977, 16 days before Voyager 1. Despite having a higher number in its name, the naming is not a mistake. And it is not a clerical error. It reflects the order in which the missions were expected to reach their targets. Voyager 1 was on the faster track, aimed at a trajectory that would take it past Jupiter and Saturn before angling out of the solar system entirely. Voyager 2 was given a longer, more complex route, one that would allow it to do something Voyager 1 could not. Something that at the time of launch, no other spacecraft had ever done, and that nearly 50 years later, still no other spacecraft has repeated. Voyager 2 is the only spacecraft in human history to have visited all four of the outer planets. All four: Jupiter, Saturn, Uranus, Neptune, every single one of the gas and ice giants in our solar system. Seen up close in detail, with instruments designed to read their atmospheres and magnetic fields and moon systems. Voyager 1 visited Jupiter and Saturn and then departed northward out of the ecliptic plane, sacrificing the possibility of reaching Uranus and Neptune in exchange for a closer pass by Saturn's moon Titan and a faster path toward interstellar space. It was a deliberate choice. Two spacecraft, two missions, two different answers to the question of what the solar system's outer reaches actually look like. The price Voyager 2 paid for visiting all four planets was time. Its trajectory, shaped by the gravitational assistance of each planet in sequence, took longer. Voyager 1 crossed the heliopause in August 2012. Voyager 2 did not cross it until November 5th, 2018, 6 years and 3 months later. 6 years during which Voyager 1 was already in interstellar space, already measuring the plasma and magnetic fields beyond the boundary, already sending back the data that was confounding scientists and forcing them to reconsider their models. For 6 years, the data from Voyager 1 told scientists something extraordinary was happening at the heliopause. But the story was incomplete because the instrument that would have let Voyager 1 tell the full story had stopped working in 1980. Here's the thing about Voyager 1. that almost nobody mentions when they talk about what it discovered at the heliopause. Voyager 1's plasma science instrument, the device designed to directly measure the temperature, density, and flow velocity of the plasma, both inside the heliosphere and in the interstellar medium beyond, stopped functioning in 1980, not at the heliopause, not in interstellar space, before it even reached Jupiter's orbit on the outbound leg of its journey. 4 decades before it crossed the heliopause, before any of the interstellar science happened, the instrument that would have been most useful for understanding what the heliopause actually looks like from the inside had already failed. This meant that when Voyager 1 crossed the heliopause in 2012, it did so without the ability to directly measure the plasma on either side of the boundary. Scientists could infer what was happening from other instruments, from the cosmic ray detector, from the magnetometer, from the plasma wave subsystem, but they could not measure the plasma directly. They were working around a gap that had existed for 32 years by the time the crossing happened, and they could not fill it. Voyager 2's plasma science instrument was still working. When Voyager 2 crossed the heliopause on November 5th, 2018, it was carrying a functioning plasma sensor that Voyager 1 had lost before the Cold War ended. And that instrument at that boundary produced a data set that researchers described as historic. The first direct measurement of the plasma on both sides of the heliopause, inside the heliosphere, and in interstellar space, taken simultaneously as the spacecraft actually crossed the boundary for the first time in history. 5 papers published simultaneously in Nature Astronomy in November 2019 described what Voyager 2's instruments found at the heliopause. And what they found contradicted the models in ways that were genuinely shocking to a field that had been working with Voyager 1's incomplete data for 6 years. The first surprise was the thickness of the boundary. Scientists expected the heliopause to be a relatively thin, sharp transition, a defined line where the solar wind ended and interstellar space began. Models had placed this boundary as a narrow zone, maybe a few 100,000 kilometer wide, where the hot, fast solar wind met the cold, dense interstellar plasma, and the two environments blended before separating. What Voyager 2 found was a layer, a distinct transition zone, roughly 100 million miles wide, sitting just outside the heliopause, not on the inside where the solar wind lives, on the outside in what was supposed to be interstellar space, where interstellar plasma was supposed to begin immediately. Instead, Voyager 2 detected a region of interstellar particles that had pushed inward through the helop, like roots pushing through rock. Tendrils of interstellar material extending more than 100 million miles inward from the boundary, mixing with the solar environment in ways the models did not predict. Voyager 1 had seen something similar before it crossed the heliopause, but different. Before crossing, Voyager 1 entered a region where the outbound solar wind had slowed almost to a stop, a stagnant zone just inside the boundary where the wind essentially ran out of momentum before it could push further outward. Voyager 2, approaching from a different direction and crossing the heliopause at a different point, saw something completely different on its approach. A thin layer that was nearly the same width as Voyager 1's stagnant zone, but had different plasma characteristics entirely. 2 spacecraft, 2 crossings, 6 years apart. Different parts of the heliopause, completely different boundary structures. Stadiosis, principal investigator for the low-energy charged particle instrument at the Johns Hopkins Applied Physics Laboratory, described what this meant with a clarity that captured the scientific community's reaction perfectly. The fact that both probes encountered the heliopause at almost exactly the same distance from the Sun, 121.66 astronomical units for Voyager, 1 in 119 astronomical units for Voyager 2, was itself deeply surprising. One crossing happened near solar maximum, when the Sun's output was high. The other happened near solar minimum, when activity was low. The size of the heliosphere was expected to change significantly with the solar cycle expanding during periods of high activity and contracting during quiet periods. Instead, both probes found the boundary at essentially the same distance. "We don't understand why that is," Krimigas said directly. "We do not understand why." From one of the senior scientists on the Voyager mission, with decades of data from these spacecraft, that statement is not a casual admission. It is a declaration that something fundamental about the relationship between the sun's activity and the size of the heliosphere does not work the way the models say it should. The second major surprise from Voyager 2's heliopause crossing was about temperature. The plasma inside the heliosphere carried outward from the sun by the solar wind is hot. Not hot in the sense of everyday experience. The solar wind plasma is hot in the sense that its particles are moving extremely fast, which is how temperature is defined in plasma physics. Scientists expected that as this hot plasma reached the heliopause and encountered the colder, denser interstellar medium pressing in from outside, the transition in temperature would be one of the defining characteristics of the crossing. What Voyager 2's plasma instrument measured was something different. The temperature drop, the heliopause, was sharp, much sharper than models predicted. The plasma went from the hot solar wind environment to the significantly colder interstellar medium in a zone narrower than expected. But what made this finding particularly striking was what happened to the density inside the heliosphere. The solar wind plasma is relatively thin. Outside the heliopause in interstellar space, the plasma is significantly denser. Both Voyager 1 and Voyager 2 confirm this, adding the two data points together to give scientists their first stereo measurement of interstellar plasma density. The space between stars is not empty. It is filled with plasma more than 40 times denser than the solar wind at the heliopause. But something else came from Voyager 2's plasma measurement that changed a specific and important part of the picture. The temperature of the interstellar plasma, directly measured for the first time by Voyager 2's functioning plasma instrument, was 30,000 to 50,000 degrees Kelvin, hot by most everyday standards, but far cooler than the plasma just inside the heliopause boundary, which the spacecraft's instruments had measured at tens of millions of degrees. The boundary was real. The temperature contrast was real. And the direct measurement of the interstellar plasma's temperature, impossible for Voyager 1, hiding a response to make without a functioning plasma instrument, gave scientists a baseline number they had previously only been able to estimate from theory. The estimate had been off by a factor of 2. The third surprise, and the one that Ed Stone, the Voyager project scientist at Caltech, who had held that position since before either spacecraft launched, called most remarkable, was about the heliopause itself. It leaks, not metaphorically, literally. The boundary between the solar wind and interstellar space is not a clean wall. Particles cross it in both directions. Voyager 1, on its approach, had detected what appeared to be tendrils of interstellar particles punching inward through the boundary, entering the heliosphere from outside. Voyager 2, on its approach from the south, saw something different. A trickle of low-energy particles extending outward from the heliopause, leaking into interstellar space before the spacecraft had even crossed the boundary. The leakage was confirmed from two different entry points at different times during the solar cycle in different parts of the heliopause. Whatever was causing it was not a local phenomenon. It was a property of the boundary itself. Something fundamental about how the heliopause works that was absent from every model built before the Voyager crossings. Two spacecraft approaching from different directions, 6 years apart, both finding the same leaky boundary. Different mechanisms on different sides, interstellar particles pushing in from one direction, solar particles leaking out from another, but the same underlying conclusion. The heliopause is a border that materials cross regularly in both directions. It is more like a coastline than a wall with surf running in both directions at the interface between two oceans. The Voyager probes are showing us how our sun interacts with the stuff that fills most of the space between stars and the Milky Way galaxy. Stone said in the announcement accompanying the 5 Nature astronomy papers, "The choice of words is careful and significant. Not how the sun ends and interstellar space begins, how the sun interacts with interstellar space. Not a clean separation, but a continuous, messy, dynamic relationship between two environments that do not stay neatly on their own sides of the boundary. And both spacecraft are still in a perturbed transitional region." Not yet. In undisturbed interstellar space, even at 13 and 16 billion miles from the Sun, both Voyager probes are sampling an environment that is still being influenced by the solar system they left behind. Now, step back from the science for a moment and think about what Voyager 2 actually represents in the context of the entire Voyager mission, because the Discovery story is only part of it. When Voyager 2 was given its trajectory, not the one that took it past all 4 outer planets before heading for interstellar space, that decision was made knowing that it would arrive later, knowing that it would cross the heliopause in a different direction from Voyager 1, knowing that the 2 spacecraft would provide different views of the same boundary. This was not accidental. The Voyager mission planners, working in the 1970s with computers less powerful than a modern pocket calculator, designed a 2 spacecraft mission specifically to avoid the limitation of a single data point. One spacecraft cannot tell you whether what it found is typical or unusual. 2 spacecraft approaching from different directions at different times can begin to build a picture of the whole. What they could not have fully anticipated was that the instrument that turned out to be most critical for understanding the heliopause crossing, the plasma science instrument, would fail on one spacecraft and survive on the other. That